Okay, so from now on, we are going to study the current voltage characteristics of MS contacts. So the corresponding chapter for this contents is chapter 14. So on the top side, you can see the cross-sectional view of a MS contact. And now the semiconductor part is grounded and referenced. And externally applied voltage denoted as V sub A is applied onto the metal side, and the positive current direction is defined as from metal to semiconductor. So with that in mind, let's move on to the contents, how the current is flowing in a Schottky diode or MS diode. So herein, we are not talking about the ohmic contact. We are going to talk about the Schottky diode. So forward bias, reverse bias, those two words must be very familiar with yourself. But forward bias means the voltage applied onto the metal side is higher than the voltage applied on the semiconductor side. So for example, I have applied minus 2 volt on the metal side, and on the semiconductor side, I have applied a minus 10 volt. Then this MS contact is forward biased or reverse biased. When you had a chance to take a semiconductor device class in your undergraduate school, negative bias onto the metal side means the reverse bias. Positive bias onto the metal side is forward bias. This is very long. This is really, really wrong. Why? The basic assumption to say that is semiconductor is grounded. So we should watch out what kind of voltage has been applied onto the semiconductor part. So once semiconductor part is grounded, then positive bias means forward bias, negative bias onto the metal side means reverse bias. That's true. However, without any knowledge how much voltage is applied onto the semiconductor part, we cannot claim that positive bias is identical to the forward bias. Reverse bias one is, you know, negative bias onto the metal. That is totally wrong. Okay, so keep in mind that how much voltage difference has been applied, and if as long as a higher voltage is applied onto the metal side, we can say that MS contact is forward biased. Okay, so please remember this and don't be confused with positive bias is always equal to the forward bias. That is not true always. All right. So once positive bias, no. Once higher voltage has been applied onto the metal side, we can imagine what change would be induced in the energy band diagram. So again, the plus voltage minus y direction in energy band diagram indicates voltage increasing. So now metal side, I have applied higher voltage with respect to the voltage applied onto semiconductor part here. So this Fermi energy level difference is equal to Q times VA that I have applied, this VA, okay? And now metal side is forward biased, so the energy barrier height, this energy barrier height has been lowered. In other words, those electrons in conduction band in semiconductor can easily diffuse into metal side. So since the electron is now moving from right to left, the current is flowing from left to right. Okay. Now what about the reverse bias? Reverse bias means this is voltage increasing. So lower voltage has been applied onto the metal side. So This amount of negative voltage has been applied onto the metal side if semiconductor is grounded. Then, from the perspective of those electrons in conduction band on the semiconductor part, can see very increased energy barrier height. So almost all of the electrons in conduction band in semiconductor can never jump over the energy barrier height. So the only thing that can move back and forth across the MS contact is this guy. Who is it? Yes, the electrons which has a slightly higher energy level beyond the Schottky barrier height, right? And only those type of electrons can move toward the semiconductor port so that the current flowing across the MS contact can be defined from semiconductor to metal side. Okay, so at thermal equilibrium, the energy barrier height, this guy, is defined as Q times the VBI. However, now the energy barrier height has been lowered because of the forward bias. But in this case, this energy barrier height has become higher. How much? Yes, reverse bias that I have applied. So minus minus, so that mathematically the energy barrier height has been increased. So in summary, n-type semiconductor is now grounded. At, in other words, zero voltage has been applied. Then higher voltage applied onto the metal side is corresponding to the forward bias in which the Fermi energy level of metal side is lower and Fermi energy level of semiconductor side becomes higher, so that energy barrier height has been reduced in and resulting in Q times VBI minus VA. So most of the free electrons in the conduction band in semiconductor can be diffused toward the metal side so that the direct current flow from metal to semiconductor can be formed. However, once lower potential or lower voltage has been applied onto the metal side with respect to the n-type semiconductor, then most of the electrons in conduction band in semiconductor can never go over the energy barrier height in between metal and semiconductor, because the energy barrier height has been increased by Q times VA. In other words, the total energy barrier height in the reverse biased MS contact is Q times VBI plus VA. Notice that VA is the magnitude of the negative bias that I have applied. So on the right hand side, you can see that the summary on current flow in a Schottky diode or MS diode. So current is definitely determined by majority carrier flow across the MS junction. So why majority carrier flow? Yes, now we have used the n-type semiconductor and we focused on how electrons are moved back and forth across the MS diode. Okay, so minority carriers is is not contributing to the current flow in Schottky diode. Okay, just for your information, in PN junction diode, to be learned later, minority carrier is the main key knob in flowing and forming the current flow in a PN junction diode. So on the first bullet, under forward bias, majority carrier diffusion from semiconductor into matter dominates. Yeah, this guy. Okay, majority carrier in this case, because this is n-type semiconductor, so electrons, which is the majority carrier, they will diffuse from semiconductor to the metal side. Okay, what about this? Under reverse bias, majority carrier diffusion from semiconductor to matter is negligible. However, the majority carriers from matter to semiconductor is more dominant. Okay, okay. Then you may guess the current versus voltage plot. With the knowledge that you have, you can draw this curve shape. Why? Because this total amount of electrons, 1, 2, 4, the number of electrons as a function of energy is exponentially increasing because they are following the Boltzmann distribution. So if I increase VA, in other words, this energy barrier height has been linearly decreased, say that 1 electron volt, 2 electron volt, 3 electron volt, like that. Then the number of electrons that can participate in current flow has increased by 1, 2, not 3, 4, not 4, 8, 1, 2, 4, 8, 16, 32, 64, 128, like that, instead of 1, 2, 3, 4, 5. Why is that? Because the electrons are distributed out as a function of electron exponentially. Why is that? Because density of state, because of the Fermi function. Okay, so everything we have learned, and why the electrons distribution in conduction band is significant and important in describing the current flow in a Schottky diode. You now get a concept and the physical origin why the diode can flow the current at an exponential pace when the voltage across the Schottky diode is linearly increases. Okay, so this part, the voltage across Schottky diode is linearly increasing 1, 1, 1, but the current level has been 1, 2, 4. Okay, like that. But the real base of this exponential in growth is based on the exponential one, e1, e2, e sub e to the 2, like that. Most likely 1, 3, 9, 27, like 81, blah, blah, blah. Okay? All right. What about the reverse biased one? As shown in this plot, even though the negative bias has been increased linearly, the total amount of current flow across Schottky diode is constant and very small as compared against the current flow when the diode is forward biased. Why is that? Why the constant current can be flown? Yes, take a look at this Schottky barrier height. It has never been affected by this. Even though I have applied more negative bias, the bending would becomes like that, but this Schottky barrier height never be affected by the reverse bias Q times VA. So this electron, from the perspective of this electron in matter side, can see this identical energy barrier height toward the semiconductor part. So very constant amount of current flow can be formed when the reverse bias is applied. Okay. So same thing, all the explanation that I have done in previous slide has been summarized in this slide again. Voltage drop across the MS diode. Under equilibrium condition, you can draw the energy band diagram as shown on the right hand side. The voltage drop across semiconductor depletion region is the built-in potential. So I mean like this is Q times VBI, and that is Schottky barrier height. Okay, but if VA is non-zero, so I mean the from here to here is V sub A. If VA is non-zero, then if VA is positive, this amount of, then the energy barrier height has been reduced into Q times VBI minus VA. But if VA is negative, as shown in here, VA is negative, then the energy barrier height from here to here, conduction band edges, is becomes Q VBI minus VA. So Q VBI plus VA. Okay. All right. And let's repeat to estimate and calculate quantitatively the depletion layer width W, but with VA is non-zero. Last time, in movie clip number one, we have found and we have derived the potential as a function of x as written in this equation. And when the x is 0, at thermal equilibrium, the was minus VBI. But now, since VA is non-zero, we should take into account the VBI minus VA. So using this boundary condition, you can plug in here, x is 0, x is 0, and this left-hand side is equal to minus VBI minus VA. Afterwards, you're gonna rearrange all the terms with respect to W, then you're gonna derive this equation. And again, with the heavily doped semiconductor, the depletion layer width has become narrow. However, with the forward bias, reverse bias, the depletion layer width has been affected. So what is that? With forward bias, the depletion layer becomes narrow. But with the reverse bias, the V sub A is negative. If this value is negative, then there is minus sign, so total value is positive, so W is increased. So in other words, for a given MS diode, if we apply negative bias onto the metal side, or MS diode is reverse biased, then the depletion width becomes wider. Okay, so quantitatively, using this equation, you can estimate the depletion layer width for a given doping concentration in semiconductor. Okay, all right. And this slide is to give you some idea the depletion layer width for p-type semiconductor. The previously I have used the MS diode when the semiconductor is n-type, but now what if the semiconductor is p-type? Any change in the equation for depleted layer width as shown in here? Not too much. Instead of ND, I have used the N sub A because this is p-type, and instead of VBI minus VA, I have used different polarity. That's it. But physically, the physics behind the MS diode with a p-type semiconductor is very identical. So take a look at here. Increasing VA, W increases, increasing N sub A, W decreases. With a heavily doped semiconductor power depletion layer width becomes narrow, which is same, and W increases with the increasing V sub A. Yes, okay, all right. So I guess time is almost over for this week. I guess in the next week, I'm going to give you some more derivation steps for diode equation. So let's take a look at the final result of this diode equation. This the current value across the MS diode is the function of applied voltage VA, but IV is exponentially dependent. Okay, if I draw this equation in this two-dimensional space, the curve would becomes like that. So we're gonna learn some more details how to derive this diode equation. Okay, but from the lectures today, uh, you should draw the energy band diagram when the MS diode is forward biased and reverse biased, and you should physically explain how come the current flow has been exponentially increased when the forward bias is linearly increased. And on the other hand, when the reverse bias is linearly increased, the total amount of current flow across MS diode is quite constant and very minimal. So those two physical events, depending on the forward and reverse bias, you can have diode equation. And I didn't explain some more details how to derive the diode equation to be left to further job next week. But this week, you should understand the physics and the curve shape. of Schottky diode IV characteristic. So current voltage characteristic, IV characteristic, is very significant and important. Okay, so please read chapter 14 and study some physical origin and physics behind the Schottky diode. Okay, all right, that's all for the lectures this week, and see you in the next week. Bye bye.